Hi everybody, this is Konstantin Läufer, your programming languages instructor at Loyola University Chicago. And the purpose of this video is to get you up to speed for project 3A. And this project is to be seen in the context of our impending study of programming language compilation and interpretation. And I just added a little Trello card for week 8 that gives you an overview of this tool chain. I will flesh out this card over the break, but this will get us started. And what we're looking at is what happens when you write a program in source form. So it's basically a string stored in a file, and you ultimately want to execute the program corresponding to that source. And before this execution can occur, this tool chain needs to do some work and take what you have through various stages with intermediate artifacts. So as I said, the source code is basically a string stored in a file, and you work on this using a text editor or an IDE typically. And when you build your project, then the compiler for the corresponding language that you're using will get invoked. And the compiler has these various stages. So in Scala, you would be invoking Scala-C, which SBT does for you. And so does your IDE. In Java, you might remember at some point having invoked Java-C to compile a Java source program to bytecode. And we'll talk about that as well. In any case, what this type of compiler does is first it looks at your program source just as a string. It reads it from the file. And it performs what's called lexical analysis, which means taking these characters, which is basically an unstructured sequence of characters, and grouping those characters into tokens. And a token could be an identifier, token could be a punctuation, such as a comma or a period. A token could be a number, a numeric constant. A token could be a string literal, meaning a string delimited by quotes, that type of stuff. And what you have after lexical analysis is a sequence of tokens as opposed to this initial sequence of characters. And based on this sequence of tokens, the next step, which is syntax analysis, is going to be easier. So what we have is this linear, as sequence implies, a linear sequence of tokens, and we need to put more structure into this. We need to organize it as a tree, and that tree is called the abstract syntax tree. And the stage of the compiler that's responsible for that is called syntax analysis, or widely known as parsing. And the kind of syntax tree that we get will look structurally very similar to the other kinds of tree examples we've studied, such as the composite shapes or org charts. But the best starting point really for looking at program interpretation and execution is the expressions example. So therefore, project 3A builds on the expressions example. We'll get to this momentarily. What we'll be doing is extending the expressions example with constructs that you would more typically find in an imperative language. So we'll have assignment, we'll have a sequence of statements, we'll have conditionals and loops. So we'll get to those details. Just to wrap up the different stages of the tool chain. Okay, so once we have an abstract syntax tree, we're in pretty good shape, because from that we can then ultimately generate machine code or byte code that can be executed in some suitable way. Okay, so what we can do first on the syntax tree is do various checks, looking at the tree in different ways. So for example, check whether things are used in a way that's consistent with their type. So that would be something that all statically typed programming languages do. So Java, C, C++, C#, Scala. And then we could do some optimization, such as common sub-expression elimination or various other more sophisticated types of optimization. And that gives us still an abstract syntax tree, but it'll be more transformed compared to the original one. And once we're happy with those results, then we can go on to the next stage, which is generating either native machine code or byte code from the abstract syntax tree. So all of these things are similar kinds of operations. They can be implemented as similar kinds of operations that we've seen in the other examples. So a tree transformation would be more like a, in some cases, in simple cases, it could be like a map where each node in the tree would maybe get annotated, but the structure would be preserved. But in the more general cases, it would be more like a fold where the structure would be altered, and we would basically traverse the tree and build up a transformed tree in the process. So code generation would be also a kind of a traversal where we'd be pumping out the target code based on the traversal of the tree. So that would be in terms of traversal strategies, it would be also a type of fold or catamorphism, because we're building something completely new from the tree. Okay, and once we have the machine code for our target hardware, we could just run that as a program, just like a C program. And if we have generated byte code that has to be executed in a managed environment, such as a virtual machine, then we would have to launch that code within a virtual machine environment. So it's very similar. The main difference is when you're executing machine code, you have a physical machine, although that's not even so true anymore, because a lot of the servers and other machines where you would execute your code are virtual machines themselves. But virtual machines representing physical hardware machines with a specific hardware architecture, such as an x86 architecture. Or on the bytecode side, it's typically to abstract away differences in physical hardware architecture, and that's when you need an actual bytecode interpreter, which is basically what a virtual machine is. So the program execution would be a separate step. Now, as an alternative, a simpler alternative, we could skip that second half of the tool chain, which is known as the back end of the compiler. And once we have the abstract syntax tree, maybe do a little bit of checking and optimization, and then directly interpret the syntax tree and get our results in that way. And that's the route that we're exploring here in this course, because it's simpler, and this is not a full-fledged compiler course. We're just trying to get the minimal exposure to this set of topics needed to make good sense of programming languages and better understand the choices and the design space. Very good. So let's now move over to our example. And we reviewed this briefly in class. This is project 3A. Project, rather. The example is tied to this project. And here we're focusing on just the first two steps of the front end. So just lexical and syntax analysis, but not interpretation. Interpretation will be the subject of project 3B. And in the past, conventionally, well, in the present as well, but more conventionally, lexical and syntax analysis were done as separate steps using separate tools, and those tools could be relatively complicated, and the syntax analysis was typically based on what's called context-free grammars, which are quite powerful. And recently, parsing expression grammars have emerged as an alternative to context-free grammars in the numerous simpler situations we have when just dealing with computer languages. And EBNF here, meaning extended Backus-Naur form, is a notation for describing grammars, and we'll see examples just coming up below. And many of those, when done right, can be expressed as parsing expression grammars in relatively straightforward ways. So again, project description. So we'll be writing just this combined front end, lexical and syntax analysis combined. No type analysis or other optimizations or anything on the abstract syntax tree. So just going from textual source to the abstract syntax tree. That's the goal. Okay, what we'll do now is take a quick look at the expressions example. And I got that here. Actually, let's do the demo first. So if you check this out, you should be able to run a main called calculator here. Okay. And let's start that up. And it allows us to enter an infix expression such as 5. And in general, when you write these kinds of things, they should be able to handle extra leading space, extra trailing space. Let's see if ours does this. Yes. So yeah, it's very simple. You can just trim off the extra space. That's very easy to achieve. And what it tells us is what we entered. So it echoes back the input, and then it tells us what our parsed expression is. And this is not meaningful right here, but we'll shortly see what that looks like when we enter more complex expression. And it tells us a few properties of that expression. And what it evaluates to, well, so far this was trivial because numbers evaluate to themselves. But what if we have a more interesting arithmetic operation such as addition? So we could have an addition, or yep, and here it tells us, okay, it evaluates to the right result, and it printed something that looks more like a tree. So this is the direction we're heading in, okay? So this infix expression 3 plus 5, where plus is an infix operator, gets parsed into an abstract syntax tree with the operator at the root and the sub-expressions of that operator as the leaves. And that's what this notation represents, right? So indentation is used to represent, just like when you're looking at Windows Explorer or file system in a tree view in general. So if we have something more complicated, let's say 1 minus 2 times 3 plus 4. So we should have this top level multiplication at the root, and then we should have subtrees representing these sub-expressions. Okay? And that's exactly what you're seeing here. Okay? And, well, we better check that this evaluates correctly, and yes, it does. So 3 plus 4 is 7, and then 1 minus 2, negative 1, so there you get the negative 7. Okay, so what we're seeing here is kind of a calculator REPL. REPL, as I'm sure you know, means read, eval, print loop. And when we're done, we can just hit our end of file character. So on Mac, this would be Control D, and we're done. And there's an extra credit for being able to use your arrow keys, you know, a kind of read line or J line thing that you usually have, for example, here in your terminal, right? So having that kind of thing is a common feature in REPLs. And you could use J-line 2 and achieve this without a lot of extra effort. So you're encouraged to give that a shot. And now we can actually look at the code. You know, how is this whole thing made possible? Well, what we need is really two things. So we need to have a representation of our abstract syntax tree and this kind of stuff. It looks just like the other examples I mentioned, shapes, org charts, and whatnot. And again, here this is a recursive type. So, for example, these binary operators are all defined in terms of the expression of which they are a special case. Okay. There's also this U minus, which means unary minus. That has just one child because it just adds a negation to an existing expression. And then expr is just the common underlying abstraction. And then constant represents numbers, so that's for leaves in your trees. Everything else would be an interior node. Okay. And you might wonder, where are the parentheses? Because here we had expressions with parentheses. Well, the point is the abstract syntax trees are tree representations of expressions where the tree structure indicates the order in which things get evaluated. Whereas in infix expressions, you need the parentheses to indicate, for example, that this addition, 3 plus 4, should be evaluated before the multiplication. Okay, so the need for parentheses goes away when you represent things in this more structured way as expression trees. All right, but okay, in the concrete syntax, however, meaning source level syntax, we have to deal with parentheses. So what we'll look at next is the parser, which is responsible for producing instances of these abstract syntax trees. So the parser looks like this. And this uses, and there is a false error here. There are situations where the IDE just doesn't quite get it right. So as you saw, the program ran, compiled and ran fine. So this is definitely a false positive. Anyway, we'll have to ignore that for now. And what we're defining here, so we're using the parboiled 2 parser generator for pegs or parsing expression grammars. And then this is our abstract syntax tree we just looked at. And now here we need to define a subclass of the parser class that parboiled provides. And that takes a parser input as its argument, constructor argument, so that becomes an instance variable. And then typically at the top level, we'll define a rule for input line. So everything that we see now is a grammar rule. That's what the parser consists of. And these rules describe the recursive structure of the language. Okay, so this rule construct also comes from Parboil 2, and all these other constructs do as well. So we can say, well, an input line is 0 or more leading spaces followed by an expression and then followed by the end of input. And there's a way we're dealing with trailing spaces further down. Okay. Now the first rule we'll implement is, and see, these match what we have here in the project description. So an expression could be a single term, and then these curly braces are for grouping, and the asterisk is a so-called clean star. This would be K-L-E-E-N-E as opposed to Mr. Clean. So a clean star means 0 or more occurrences. You might have seen this in other classes, maybe in 163. So what we're seeing here is a single term followed by 0 or more occurrences of either a plus or a minus and another term. So you could express, for example, just a term like a number 2, and then you could have +4, -7, that kind of thing you could build. But then we'll see that terms could be other more interesting things than just numbers. We'll see that in the next rule. Okay, so how does that translate? How do we represent this formally, programmatically, using a parsing expression grammar in Parboil? So we'll say, okay, it's a rule. We'll have a rule for expression. And we'll have a term, and then 0 or more, so that's the way we represent the clean star, 0 or more, either a plus followed by a term, or, and the vertical bar means or, it's pretty common, or a minus followed by a term, and the twiggle arrow means what needs to be generated as a result when this rule matches what you're seeing in the source. So this means if you're seeing a plus followed by another term, then we'll create an abstract syntax tree using those constructs from our abstract syntax tree, where the first thing, each underscore is a separate implicit anonymous argument being passed in. I could have made them explicit, but it doesn't add to the readability. I could have said x, y, and then plus x, comma, y. But this is equivalent, and the names x and y wouldn't really have much of a meaning, although we could have said, I guess, left sub-expression and right sub-expression. And for one of them, we have to say what type it should have, otherwise the Scala type system gets confused. So those are kind of design trade-offs. It's a fairly powerful parser generator, domain-specific language. So in any case, if we see the plus followed by another term, we'll put whatever the first term generates here. We'll put whatever the second term generates there. And the plus itself is a so-called terminal. In a grammar, a terminal is basically a literal symbol that you find in source, whereas a non-terminal is something that needs to get parsed further by applying some other rule. So term is a non-terminal. So it's a term in the algebraic sense, in an arithmetic expression, whereas the operators are terminals here. Okay, so the two non-terminals evaluate to some sub-expressions, and those results get stuck in here. and then the plus gets placed at the top as the new root node for those two children. And minus is analogous. And now the question is, well, term, what exactly is a term going to be? So we need a rule for that. And here is the rule in kind of high-level pseudo code or BNF. A term is a factor followed by 0 or more of these more multiplicative operators like multiplication, division, or modulus, and another factor. Okay, so here we could have something like 3 times 5 modulo 2, that sort of stuff. Okay, and the structure of this rule is very similar, and we'll have factor as the non-terminal for the left and right sub-expression. And then depending on the kind of operator we're seeing, we'll take whatever we have and then stick the corresponding node from the abstract syntax tree at the root. Okay, so you might ask, what if we have 2 times 3 times 4? Well, the first multiplication becomes the actually, you know, let's experiment with that. That's even better. So, because if we enter that here, we'll get the tree structure that it generates back immediately. So let's try it out. Two times 3 times 4, and see, so it builds the little kind of like a chain of times nodes, and what it does is it does it in reverse order, so to speak, meaning the root is the rightmost operator it sees, and that makes sense because, see, every time it goes on toward the right and sees another operator, it creates another root on top of what it already has. So that's consistent with what you're seeing here. Okay, now finally, okay, factor is still a non-terminal, but factor looks really more like a kind of leaf, or at least somewhere where we want to have leaf-like things. So for factor we have a rule, and that we had to type to get it to work. Type explicitly. Factor is either a number, that would be a number, numeric, literal, or a unary plus followed by a factor, or a unary minus followed by a factor, or we could turn any expr into a factor by putting parentheses around it, and we've already seen that. And now we implement this in parboiled in this way. And we introduce a few more non-terminals for which we have to have rules. And a good style is to capitalize the non-terminals. So number, we capture digits, and digits are defined down here. So one or more characters to which the digit predicate applies, which is a predefined predicate. And then we can have 0 or more digits after a number. So there are places here and there. This is kind of a way parboiled and other parser expression grammars work. The lexical analysis is kind of integrated in the syntax analysis, so you cannot easily skip whitespace as a separate step. So you have to have a few rules within your parsing expression grammar that deal with whitespace. So, you know, that's a little bit of a drawback, but there are other benefits. The simplicity compared to context-free grammars. Although when you look at simple examples like this, you don't really see that much of a difference in complexity. Okay, so what we have is, you know, what we're looking at is 1 or more digits, and then 0 or more spaces, and that generates a from what we get, the digits come in as the string s. And we'll have to create a constant leaf node in our abstract syntax tree, and that wants an int. So we have to convert the string to an int using toInt. Okay. The other ones are easy. The unary plus basically just ignores the plus terminal. And the unary minus, well, that has a meaning because it negates the value, and we have to create a new root of node type unary minus, u minus. Now, parentheses, again, those are just meaningful in an infix concrete syntax expression. They just denote the expression themselves, or itself. So, in other words, when you're parsing a sub-expression, a parenthesized sub-expression, you're just then generating the subtree for that expression. So the parentheses get ignored. All right. These rules, again, this is a parboiled thing. I don't want to go into too much detail, but it's the recommended practice for automatically handling trailing white space after single character and string terminals. Okay, so this kind of avoids having white space handling in more than just this number rule. So it kind of keeps it out. Implicit means it gets applied implicitly when it fits from a typing point of view. Okay, so this concludes the review of our parser. And what you saw already in action is the kind of tree that gets generated, and it's a successive application of these rules, starting with this input line rule. So there it skips the leading white space here, and then it attempts to parse an expression. So that's our top level thing, right below input line. Okay, so this ensures, by looking for the additive operators first, plus minus, it ensures that those get the lowest priority. Then the next higher priority is the multiplicative ones, and then parenthesized expressions have the highest. See, so that's why those are down here in factor. So that's how you express priorities among operators. There are other techniques for doing that as well. There's a technique called operator precedence parsing. It's more complex. So this gets the job done. Okay, now we have a few other behaviors that are not as interesting as parsing, the size and depth stuff. And then we have others that we'll look at in conjunction with project 3B, evaluation. That's the most interesting one, really. But it requires the ability to parse a source. And then these things here are what you call pretty printers or unparsers. Okay, so to-formatted string is what builds those trees. And the indent prefix, let's see, there's some definition of the indent. Yeah, that's down here. So I deliberately used dots because that's easier to count than spaces. You know, so you can really see this very easily, that there's a leading indentation. Also, to paste these things into environments where leading spaces get eliminated, it helps. You know, like in Sakai or wherever. Okay, that's that as far as the behaviors are concerned. And then the main method is here, or main class. And this is the body, or the main code. There's the loop. So it says for each input line, we process that line and then prompt for another line to be entered. And then what we do is here, these things, and we report back what was entered, and then we attempt to parse the input. So we create a new little parser instance, and then we run the parser on that, and then we get a result. So we could get a parse error failure. So let's try that. 3 plus. See, it says the expression could not be parsed because after the plus it wants another term. Okay, so there's even an error message. And it tells you what could have followed. Why does it say there could have been a plus? Well, because you could have had maybe 3 plus 3. So an infix plus and a unary plus. So that's why it says you could have had another plus there. Okay, the other kinds of errors are other non-parse error exceptions. So we'll just report whatever error we got. Unlikely to happen. And then if we succeed, then we do these various, we apply the various behaviors and then evaluate the expression. So in the project, we're focusing on the parsing, using parsing expression grammars, which includes lexical analysis. And what we need to do is extend the grammar to include, first of all, variables. We're building a language that we're codenaming MiniC because syntactically it's quite a bit similar to C, but semantically it'll be, once we add more stuff in project 3C, we'll add more interesting capabilities. It'll be really more like a mini Python, like a super mini, nano Python. Maybe we should call this nano C. It's just really stripped down. So we need to add support for variables because we'll want to have expressions such as 2 times x. And we'll need a rule for that. And then we'll want to add support for the things I mentioned earlier that can be classified as statements. So a block is a sequence of statements, one or more. A conditional is just like your typical C or Java conditional with an optional else. So usually the square brackets indicate that something's optional. And notice here the curly braces within quotes are literals, and the ones outside quotes are, of course, part of the grammar language that are just for grouping, as we discussed earlier. And then we'll have a while loop and an assignment. And assignments are terminated by semicolons. And we can also turn an expression into a statement. That'll play a role later on by adding a semicolon to the expression. So your job is, above all, to extend the parser. So you'll start with this project, and then you'll extend the parser and add rules for these new constructs and hook them into the existing parser in the right way, in such a way that the top level construct should be a statement. And you can have an expression within that statement in this way. So any expression is also a statement as long as you terminate it with a semicolon. And then conditionals and loops don't need a terminating semicolon because they have these nice delimiters in the form of curly braces. Okay, so that's this job. So extend the abstract syntax tree to support the imperative construct, meaning you go in here and add constructs that are capable of representing these new constructs, and then you extend the parser. So then you extend this parser to have rules that look for constructs with syntax given here and produce the corresponding abstract syntax tree nodes. And then also extending the pretty printer to support those constructs. Again, the pretty printer was one of the behaviors here. So the only behavior you don't need to worry about. You might want to extend size and depth, but you don't. They're not that exciting. And for now, we're not doing anything with evaluate. So you should not attempt to evaluate, because you'll get a case match error for not having branches that match the new constructs. So you'll unhook the evaluator from the REPL. So the unparser, you'll want to print things in a certain way, and you'll probably want to print the string, the expressions in the original infix notation. Okay, and I'll have to update this project description accordingly. It'll look a lot better. And then you'll want to have ways to print the statement in formatted ways. So the if should look the way you would actually write it, using reasonable coding standards. Okay, and then these are some concrete examples that involve statements. And don't worry about the fact that, for example, in the third statement here, or program, the variables aren't initialized. That's not a concern right now. That'll become a concern when we actually start executing abstract syntax trees representing these programs. Or I should say interpreting them, which is a kind of execution. Okay, so we'll be able to have these while loops, semicolons shouldn't matter, lines where it occurs, line structure shouldn't matter. And this I have to update. It'll be in P3. So we'll use a single repository for all stages of project 3. Okay. And extra credit, as I mentioned, JLine 2, supporting successive else-if branches, because here we would have to nest them according to this grammar. You cannot have this kind of flat if, else if, else if, else if that helps dealing with complex decisions. So that's an extra credit opportunity. And then for those of you who are excited to do something more formal mathematically, check out the Scala-mu library. There's a guiding example called Expressions Algebraic Scala, and talk to me. I'll provide some extra guidance. So this is related to the discussion we had earlier this week about having these basic building blocks and being able to represent any kind of structure, almost any kind of tree list or tree-like structure, by combining, by having just one kind of node and then having a branching construct called formally a branching functor. Remember how when we had a node where the branching was option, we got non-empty lists. When we had a node where the branching construct was a list, then we got trees. So the interesting thing, or one interesting thing, is that for any algebraic data type defined like that, we only need a single implementation of map and fold. So that is actually quite remarkable. And that's what the Scala-mu stuff is about, to be able to learn, study and learn a little bit more about those deeper structures. Anyway, so this is completely optional. I understand that there's certainly enough depth in this project without going the algebraic route, but I wanted to put it out there as a choice. Okay, so that's it for now. I'm gonna be in touch with more information soon, and have a restful and at the same time productive break. Do stay in touch if there are any questions about the project. We have to communicate and make sure we all make good forward progress. All right, take care. Bye.